Algebra 2 students. This is the video to accompany your review packet that you pick up in class today for Chapter 6. So we're all done with new content for Chapter 6, and today is your first review day. Monday will also be a review day in preparation for your Chapter 6 exam, which is scheduled for Tuesday. So in order to prepare for that exam, this is a good tool, and it's one that I would recommend that you use by trying each of the problems on your own first, and then checking your solutions against this video. So that way you're seeing what you really know on your own versus what you may need a little bit of an assist on to get started. Another thing that I would strongly recommend doing this weekend to study is that I have on the website posted some suggested textbook problems. And so if this is something that you can knock out and finish pretty quickly, I would make sure that you try those as well. That way you're touching on all topics. Because although this is a pretty cumulative review guide in the sense that it covers topics from each section, it's not exhaustive. So it's not representative of all problems that you could possibly encounter from Chapter 6. So Chapter 6 is really all about radical functions and about square roots and cubic roots and fractional exponents and how they relate to one another and how they can be simplified and how they can be graphed and how they can be solved in equations. So we're going to start this review back at the beginning with section 6.1, which is just where we were converting between different kinds of roots and rational exponents. So to get started here, we're going to take a look at problem A. So this one asks us to convert from a fractional exponent to a root operation. So if I want to convert 8 to the 2/3 to be a root expression instead of an exponent expression, what I'm going to do is bring the 3 from the denominator out to the front of the root. So I'm going to have a cubic root, and then the 8 squared is going to stay inside of the root. Then I can simplify 8 squared to be 64. 64 is a perfect cubic value, so I'm going to end up with just 4 here. Part B is going to be a very similar operation, but I do have that negative exponent to consider. So when I go to rewrite this operation, first I can move the 81 to the 1/4 down below, because the negative tells me to move that operation. Then what I can do is that 6 is just hanging out in the numerator, that's this 6 here, and I can change a 1/4 exponent to a 4th root. Now if you check your yellow list of perfect powers, 81 is going to be a perfect 4th value. It's going to give you 3, and then 6 divided by 3, that's just going to get you right there to 2. Last one here is negative 64 to the 2/3 power. So what we can do here is take the cubic root of negative 64 squared, and if we wanted to simplify that operation, we can take negative 64 and square that quantity, which gives us 4,096. 4,096, if you check your list of perfect cubic values, is going to give you a result of 16. Now that's one way to go about doing part C if we wanted to do it by hand. And the reason that I took that approach is that it asked me to convert from a fractional exponent to a root. But I think it is useful to point out that something like negative 64 to the 2/3 is something that I could simplify this way instead. What I could do is work with 64 to the 1/3 power, and I can leave the 2 on the outside of the exponent. So if you think back to your 6.1 notes packet and your 6.2 operations, this is where we did the reverse of the distribution property. The reason we would want to do this is then I can consider my inner piece as the cubic root of negative 64, and then I can square that quantity. 64 is a perfect cube, and then if there's a negative, it's just going to bring along a negative with it, and I'll end up with negative 4 squared, which is also 16. So it's going to check out either way. Then in problem number 2, we're going to be solving some equations for x, and these are ones that looked really fantastic on our quiz, so these ones should still feel pretty easy in review. So if you look at A, you have x cubed minus 11 is equal to 83. So the first thing that we want to do here is to add over that 11, and we're going to get 94 when we do that. Then to get x by itself and undo the exponent, we're going to take the cubic root of both sides. Now these particular instructions ask us to round to one decimal place, so we're not going to report in exact form, we're going to report in approximated form. And when I take the cubic root of 94, I end up with a result of 4.5. And again, the determination to leave something in exact form or to approximate generally depends on the context. So the more theoretical work we do, the more we tend to leave things in exact form, so we maintain that precision. But if we're doing applied examples and we're solving for a distance or a time value, that's when we typically round. Now, if we take a look at B, this one's just a little bit different because an entire binomial is being raised to the fourth power. So here what we want to do is take the fourth root to undo that fourth power. So then I'm going to be left with x plus 2 here, and then I have the fourth root of 21. And so if I get a 1 decimal place approximation there, that's going to be 2.1. But what I want to be careful of is that there's really a plus or minus out in front here because it's an even valued root. So that means I'm really solving two equations. I'm solving x plus 2 is equal to positive 2.1, and x plus 2 is equal to negative 2.1. So when I subtract 2 here, my first solution is just going to be 0.1. And then when I subtract 2 here, my second solution is going to be negative 4.1. So for even valued equations, I'm going to end up with, even valued root equations, I'm going to end up with 2 solutions. Odd valued, I'm just going to end up with 1. Now we've got some section 6.2 material, and this is where we're going to start off by applying properties of exponents, and then we're going to do some root simplification. So part A is just properties of exponents. It's just saying if you divide two exponent expressions that have the same base, you need to decide what it is that you're going to do with those exponent values. So we can subtract when we divide exponents anytime they're the same base. And what we want to note, is that 8 all by itself is really just 8 to the first power. So when I check out these exponents, what I'm really going to be doing is taking 1/3 and subtracting off 1. Now those do not have a common denominator, so I need to make that 1/3 a fraction, which is going to be 3/3. So this is going to be negative 2/3. So my result is 8 to the negative 2/3, which I'm going to write as 8 to the 2/3 power. Now if we wanted to simplify that, 8 to the 2/3 is something that will work out perfectly and something we saw earlier. So I can reduce this to 1/4 simply because this value is one that results in a nice perfect integer term. Now the one key thing I think we should watch out for here is that when we divide these guys, the exponent subtraction takes care of the division. So I don't also divide the bases of 8. So I'm still going to have an 8 in this result here. It doesn't ever reduce to 1, which I think is an easy mistake to make. Then let's take a look at B. We are trying to simplify the square root of 45. So this is where our perfect powers list is going to come in handy again. Because what we want to do is figure out what perfect squares divide into 45. And the result that you're going to find is 9 and 5. Square root of 9 is going to give you 3. And then the square root of 5 is left inside of the square root operation. Letter C, we have 2 cubic roots multiplied together, which is just fine to have. We're going to go ahead and multiply each of the numbers that are underneath the cubic roots together. And that's going to give me the cubic root of 686. So the first thing I would want to check is whether or not that is a perfect cubic value that I could simplify. If you try that in your calculator, it's going to give you a decimal, which tells you that it's not. So instead, I want to check and see, are there any perfect cubic values that would divide into it instead? And so what I see is that the cubic value of 7 cubed, which is 343, does divide in. So I can make this 343 times it's going to go in twice. At that point, then what I can do is simplify this cubic root operation, because the cubic root of 343 is 7, and then I'm going to be left with the cubic root of 2 because I can't do anything else with that. So that's our final answer for part C. We've got 3 more simplifications, all that are dealing with roots. So let's check out what's happening with D. Here we have one square root times another square root. So we are just fine to multiply everything together underneath one square root and then simplify from there. So I want to multiply my constants together, the 200 and the 3, which is going to give me 600. Then when I multiply, I still need to make sure I add my exponents. So x squared and x to the 8th will become x to the 10th. And then y to the 4th and y to the 4th will become y to the 8th. And then this is a square root operation. So thinking ahead, my exponent values are going to be just fine to simplify here. The only thing I need to consider is the square root. So I would recommend breaking apart this 600 into the closest square root value that will divide in there. So in this case, that's going to be 100. So 100 times 6. And then I have x to the 10th and y to the 8th. Now that 100 is a perfect square, so we can bring it out in front as a 10. This 6, though, can't do anything with that. I'm going to have a square root of 6 in the problem. X to the 10th, I'm going to divide this 10 by this 2, so I'll end up with x to the 5th. And then my y value, y to the 8th over 2, will give me a y to the 4th value. And that's going to be my simplified result here. Letter E is really similar. The only difference is this is a cubic root instead of a square root. So I'm going to go ahead and break it apart and see what's going to work and what's going to be left inside of the root operation. So I'm taking cubic roots. If I check 189 in my calculator, it is not a perfect cubic root. So instead, what I need to do is start trying to divide things from my list of perfect factors. So I can try 8, and then I can try 27 or 64 and see what's going to work. When I divide these out, I see that 27 divides into 189 7 times. Then x to the 12th is going to be fine as an exponent. So is y to the 9th. But the issue here is going to be z to the 11th. I need to break that up into z to the 9th times z squared to simplify. So now I can start to bring terms out in front. This cubic root of 27 is going to become a 3. But then 7 is going to be left inside of the cubic root. X to the 12th, when I divide by the 3 out in front, will become x to the 4th. Y to the 9th will become y cubed. Z to the 9th will become z cubed. And then we'll have 1z squared left back inside the cubic root. So I can box this one up. And that's as simplified as we can possibly get there. The last one from this section involves some addition and subtraction of square roots. So it's just going to be 3 different mini versions of the previous kinds of problems all put together. So 162 is not a perfect square, but I can break it up into 81 times 2, and that works. Then 147, that is also not a perfect square, but it is divisible by 49, which is, so I can write it like this. And then, oops, I've got a plus sign, not an equals. 50 is also not a perfect square, but I can write it as 25 times 2. And now I can begin to simplify, because this square root of 81 is 9, and 9 is going to multiply by this 2 out in front to become 18 times the square root of 2. Then this square root of 49 is 7, which is going to multiply by this 8 out in front to become 56. And then over here, this 25 square rooted is going to be 5, which if I multiply by this 4 is going to become a 20 times the square root of 2. At this point, I can only add and subtract roots that are both alike in index and also in the contents that are inside. So the 18 root 2 and the 20 root 2 can combine. 18 plus 1 and 20, or 18 of one and 20 of the other will give me 38 times the square root of 2. And then I'm subtracting off 56 times the square root of 3. So once you finish checking your solutions from this video, go ahead and open up the next link, and that will get you started with section 6.3.